welcome to the afternoon session of growth for lunch. Your speaker now is Jacob Leamer from the University of New Orleans, who will tell us something about quantum discord.
Yes. Hello, everyone. As I said, my name is Jacob Leamer here. This is some work on developing a class analog for quantum discord that we've done over at Tulane or the Dartmouth group. So we're going to go ahead and get started. Feel free to ask questions, but first, just an outline of the talk.
I get to talk about.
Okay, yeah, sure. So first, we're going to begin with just an introduction of what we mean by quantum discord, at least as like a verbal definition. We'll then go into a little bit about the mathematical formulas behind it, give a bit more concrete definition. We'll then talk about how we can begin to construct this classical analogy before describing our experimental setup, the results, and then we'll have a few quick remarks. So first, introduction.
Here in the back. Yeah.
Okay. The question is, what is quantum discord? And quantum discord was proposed by Olivier and Zurich back in the early 2000s. And as the title says here, it serves as a measure of the quantum correlations, or it serves as a measure of non-classical correlations of existing systems. And this was proposed after it became apparent that there were many situations in which quantum mechanics, quantum systems outperform classical systems, despite the fact that there was little to no entanglement. And for much of quantum mechanics' early years, it was believed that entanglement was the thing that made it distinct from classical mechanics. And so, in recent years, we've seen it be used in a large variety of contexts, mostly in quantum information theory. And so here are just two examples. Paper discussing its use in quantum cryptography, uses a resource for remote state preparation, which is like quantum teleportation, but different in that the sender, Alice, knows her state classically from Bitcoin. It's also been used in quantum metrology and in quantum state merging. And a lot of these, there's also been some implication for quantum communication tasks that discord is more robust to noise from the environment than entanglement. So it might have applications for long distance communication. But to talk about the definition of it from an information theory perspective, we need to go ahead and start at the beginning a little bit. And so two very important concepts in quantum or in information theory in general is entropy. And here entropy has the meaning of the uncertainty in the measurement or the outcomes of random variables. And so this plot here is just the entropy of a simple point, as the probability of flipping heads is varied from 0 to 1. And so because this is a classical system, we define it using the Shannon Entropy, which is here, which is for a random variable with n possible outcomes. The entropy is the negative sum of the probability of the individual outcome times the log base 2 of the probability. Quantum mechanics, this is the von Neumann entropy, which is given in a very similar fashion as the negative trace of the density matrix, log base 2 of the density matrix. And so here we see that at the probability of 50%, the entropy is at its maximum, which is 1 bit. This is where the uncertainty in what you're going to get when the outcome is maximum. But it gets more interesting when you consider two systems that can be correlated. And so if we represent all of the information that, or the entropy of A in this blue circle, and the entropy of B in this orange circle, we can define a quantity known as the mutual information, which is I of AB. The I of AB serves as a measure of how independent these two systems are. If it's 0, the overlap here is 0, and the two systems are completely independent. But if it's not 0, then there is some dependence between them. And so we can obtain this by just taking all the information in A, all the information in B, and then subtracting the union of these two sets. Because we double counted this overlap by these two, this just leaves us with you. Another possible way of obtaining mutual information is to define something known as the conditional entropy. The conditional entropy tells you the uncertainty in the outcome of A, for instance, in this case, based on something you know about the outcomes of B. And so this quantity is the blue circle that's not in this overlap. So the entropy of A conditional B is here, and we can, if we use B in this case, we can define the mutual information for this overlap as just this section of the circle subtracted from the entire circle. Now, the key difference is that quantum mechanics and classical mechanics disagree on if these are always equal. In classical mechanics, they are always equal. But in quantum mechanics, they're not equal generally because measurements in quantum mechanics are basis dependent. And so the conditional entropy depends on how you measure the outcomes of B that you're using to know something about A. And so this means that this quantity takes on sort of a measure of the classical correlations for the basis unit. And with that in mind, we can go ahead and define the total classical correlation of the system as the maximum of this quantity over all the possible orthogonal bases that we could have measured A with in this case. And so the discord as defined by Zurich is just the mutual information from this normal definition minus the maximum classical correlation of the system. And this has been what's commonly used in a lot of these quantum discord applications. So some interesting things to note real quick is that this is not symmetric. It's possible for the discord of B with respect to A to not be the same if you invert the order in which you consider these arguments. But now we want to go ahead and talk about how we can begin to develop a classical analogy for these things. And so first we're going to just explain that we consider the Bell states as the quantum state to be sort of analogized. And here we just have the Bell diagonal states, which should look very familiar. Here's a mistake, actually, this should be smaller. But the density matrix form of this is just given here. And this is, we include this because we need to calculate the von Neumann entropy from the beginning. And then this plot here is the block sphere with the points of vectors that have non-zero discord highlighted. And so the scale here is the magnitude of the length of that vector, or magnitude of that vector. So the red dots exist on the surface of the sphere. Their magnitude is 1. They're the pure states. And the blue dots are in the center. They're the mixed states. And so we see that we get some very interesting structural patterns sort of in this, which is just a very interesting image to look at. We have these regions of like concentrated discord values with these gaps here that don't have any discord whatsoever. Yeah, so this is just an interesting plot. Are there any questions so far? I should make sure. Good? Okay. Sorry about that. So then, how do we construct a classical analogy for something like this? And this isn't something that we've done that's new, but to just walk you through it, if you consider sort of electric field as a function of the direction, the position perpendicular to propagation, and the time. We have the temporal component here, and we have this double sum over the spatial component with a vector that describes, in this case, the polarization of the light. And we're summing over H and B in this case. And the G sub LM here is supposed to be suggestive of the Gaussian modes. And so we can include all the higher order ones in principle. And this formalism can be very easily represented as sort of a state vector sort of fashion, where we've replaced the explicit functional for with this E in a parenthesis. Where we've also done the same here, and we replaced the vector hat notation for just J. This is very, very similar to the notation here in quantum mechanics, where we use kets instead of parentheses. And so, in this sense, this can be considered sort of a C bit, if you want to consider that a classical bit, whereas this is more like a qubit notation. And so, these are basically equivalent mathematically. And so we can treat things here, we can treat here, vice versa. That's the idea.
Yeah. These are orthogonal. GLM and J are orthogonal. Does GLM form an orthonormal basis?
Yeah.
Are they spherical harmonics? Are they the spherical harmonics? Or
so it's just supposed to be general representation of like higher order Gaussian modes, like the Hermite Gauss modes. And it's just the combination of the spatial part of the electric field. So we've sort of separated it into polarization and spatial components. This is very similar to the Jones calculus formulation of the electric field, where we explicitly considered the spatial components as not being.
I am confused because it's a discrete sum and not an internal. But in three-dimensional space, no boundaries, most will be continuous, right?
So these are, so this is a continuous.
Considering solving the electromagnetic wave, like described solving under there are some contradictions. The GLM is the general, like it depends on what kind of space they're looking at. The Fermat polynomials here, and they will get a different space.
Yeah. So for example, the Laguerre-Gauss modes are the solution to the Maxwell equations for cylindrical coordinates, and that's the Hermite Gauss modes are equivalent, but for Cartesian coordinates, but higher order modes than just the Gaussian. G00 is just the fundamental Gaussian mode. G01, for instance, would be one of the first higher order Gaussian modes. And so this contains all the spatial part of our electric field here, and this is just the vector direction. And so this is very similar to the Jones calculus formalism, which is already known to be very similar to the sort of block sphere representation. The Jones calculus is used to create vectors on the point gray sphere, which is an analogy to the block sphere. Any other questions? Okay. So yes, so now that we have this classical sort of analogy to these quantum states, we can go ahead, and this is not something that's new to us. This has been well established in the literature. In fact, the use of parentheses as a version of classical cats comes from Robert Sprew. He calls it parent in a thesis. Everly has done a lot of work in exploring the correlation and coherence of classical optics and remarking of the mathematical similarity to similar things in quantum mechanics. And this has also been used in experimental demonstrations of things. We, for instance, were able to experimentally violate the Leggett-Gargan inequality using the polarization of classical wave. And the Leggett-Gargan inequality is a temporal version of the Bell-Leggett inequality, where the correlations are between the measurements of the same system in time, like at different times. And so there's a lot of use that can be obtained from constructing these analogies and exploring how the math works in each case. So in our case, we're specifically going to use the LG spatial modes, which have this representation here. So we're ignoring the polarization explicitly. But we have bell diagonal state, we have the quantum 0, 0, 1, 1, which again, I guess I have to type it. But here we have the LG 0, 0, 1, 1, and then we have the LG 0, 1, and LG 0. But to make things a little bit simpler going forward, we can still obtain states with non-zero discord if we arbitrarily set two of the eigenvalues of the Coherency Matrix rho BD to 0. And so our analogy, rho LG, we're just going to take psi plus and phi plus. And then we can still get non-zero discord states, but this is a lot easier to implement experimentally. Yeah, sure.
I am confused by the analogy because to me, what is analog to a quantum state is the classical analog is an element of the classical phase space. It's your full information about the state. And that requires the field and the conjugate momentum. And you are only given these states on the right and only about the field itself.
The key difference between, and this might address your question, the key difference between quantum states and classical states is that creating a state like this in quantum mechanics can be separated, right? I can take these are two independent qubits, right? The entanglement that happens in classical optics is between different degrees of freedom of the same object. Does that make sense?
That makes some sense.
Yeah. So for instance, one of the very a simpler way of doing this would be to take light and then you would polarize its position and its polarization into two different beam paths, right? So if you use the beam splitter to separate light into two different paths, the position of the beam is correlated or entangled with the polarization in that beam. But you can't separate those, right? There are 2 degrees of freedom for the same beam. And so you can't take the polarization and move it somewhere else and measure it and see what the position was.
But the question is, what do you need? The conjugate momentum of the electric field, which is the magnetic field or the electric potential.
I mean, if you have
Right, classical.
so the LG modes for the electric field also describe the magnetic field, right? Like by the relations of Maxwell's equations.
Right, but you need time in between. Just give me the electric field at a given time. I don't know what the magnetic field is, right? Time derivative of the electric field.
Sure, but the thing here is, I'm afraid I'm not sure. Like, this doesn't have explicit conjugate momentum, right? This is quantum, right?
I can ask later.
Okay.
I don't want to take it to the time.
Yeah.
We have the basic.
It's full beam. It's full
Oh,
beam,
yeah,
not just that. But also
Yeah. So this.
find out the whole LHC. I mean, but another electric field, then I have to just be.
Time derivative of the electric field.
Yeah, that's not a problem. This is the still. It's the middle way to win by the.
Okay. So yeah, so this is the state that we want, or the density optical analogy to the density matrix. And this is typical of the. This is you can also refer to this as the coherency matrix, which is often used in literature. And this forms the optical analog to the density matrix in quantum mechanics. But this requires incoherently adding together 2 of these modes, and so we need to be a little clever about how we do that. So to construct our rho LG, we first just use, I'm just using E here to represent the entire field. We can make one beam psi plus and one beam phi plus. These lambdas here serve as the analogy to the eigenvalues of the density matrix and are derived from the ratio of the intensity of the total intensity that's in that beam. So for instance, beam 1, this would be I1 over IT. Beam 2 would be I2 over IT, and I1 plus I2 is IT. And then we use a polarizer to polarize the beams into H and B, which means that they can be added incoherently. And then the overall density matrix of the LG modes with polarization would be just the thesis parent or the rocket of classical with E. And then we can re-obtain this rho LG by just taking the partial trace over the polarization degrees of freedom. This has been experimentally demonstrated as just requiring a measurement device that is polarization insensitive. So typical CCD can actually achieve this operation. And so once we have this, we're good with our analogy. And so we can go ahead and talk about experimental setup. Yes.
Would you mind if I ask a question about analogy there?
Yeah.
So, so here's the place where I'm coming from. So as we know, electric and magnetic fields satisfy the Maxwell equation. It's our second order partial differential equations, whereas the Schrödinger equation is a first order.
Yes.
With respect to time.
Yes.
Right. Now, wouldn't that make the analogy kind of like not complete in the sense that it might break at some point?
Yes.
Like, yeah.
So an important thing that we're considering here is this is sort of the paraxial solution to the Maxwell equations.
Paraxial.
So because paraxial simplifies the actual Maxwell equations considerably, and so you can obtain solutions in the fraction limit that you can obtain from like sort of the complete picture.
What would the assumption be for the Coherency case? Is it like counting
It's-
the decimal or something?
Yeah, it's basically that the path of the beam does not diverge much. Like the beam does not diverge very much across space. I can't remember the exact math. I think it's something like the wavelength over the waist size satisfies a certain condition for Gaussian beams. But yeah, and it's important to recognize that with the Jones calculus, the analogy comes because you can construct a 2 by 2 matrix. So, for instance, if you express your electric field as the x and y components, you can obtain a 2 by 2 density matrix where you have taken the average of the ex times ex star. And that would be in the top corner. And then you would have ex ey star, or ey ex star, and then you have ey star. This is analogous to the 2-level cubic density matrix, right? And so the coherency matrix of this electric field is the analogy to the density matrix. And they both describe the statistics of the system you're looking at, right? The statistics of the electric field, some decision, or depending on exactly how you do the construction and what terms you are considering. You can construct the coherency matrix, which tells you the correlation between components of the electric field, right? The density matrix tells you the statistical properties of the 2-level cubic system that you're looking at. And so because of this similarity, we can create this analogy between the correlations or the statistical probabilities between the 2 components of the electric field and between the 2-level cubic system. Okay, so it's sort of, time doesn't really enter into the equation because you consider sort of static, right?
That makes sense.
Yeah. Okay, so we can go and talk about the experimental setup. I'm going to go ahead and explain sort of what the state looks like at each point through here. I think that would make it clear. So we have the laser sending a beam through the half-wave plate and a polarizing beam splitter, which means that the only beam that passes in here is horizontal. So we have all the modes from the laser and horizontal polarization here, and we just split it into 2 different beams. The next step, we have variable neutral density filters in each beam path that allow us to tweak the lambda values here. So we can arbitrarily scale them so that we can get ratios of total intensity. Then they pass into these SLMs, which here are just considered black boxes, but they are what construct the LG nodes. And unfortunately, I'm not an experimentalist, so I'm not entirely clear how they work. But this is how they construct. This is how we construct our phi 1 and phi plus. Can't have type of system. But here,
Second H be an H or a V?
no, this should be 1, 0.
What about the second H?
The second H is an H here because then we have a half-wave plate that converts into and then we have H here. And then we recombine the beams here so that our total state is given by this incoherent sum, which means that the CCD camera image we get is effectively rho LG, or the coherency matrix of that corresponds to this. And this is our analogy. Okay, so very briefly, we can talk about some of our results.
Sorry, the experiment produces a classical state or a quantum state?
Classic.
It's all,
Yeah, everything here is classic. And this is why we're being very careful to make sure we use these parentheses rather than the text. Okay. So here, first results are the beam profiles for sine plus and phi plus. So in this case, we're taking the pictures of the beam separately so that we can compare them to simulation results. You can see that a lot of the structure is mimicked. I don't actually know how easy it is to see on this screen, but the important takeaways are that we get this ring sort of structure here that appears here, although this back part does not. And then here we get this dot with a little bit of a faint ring at the bottom, which is pretty well matched here. There are some experimental errors that make it so that they're not going to match the simulation perfectly, or at least we weren't able to. For one, we need to be able to measure all the beam parameters perfectly at the camera in order to create the simulation, because the simulation is simulating what the beam profile looks like at the camera. any vibrations in the table can cause the beams to potentially be misaligned, even by a little bit. And the theory is that they're perfectly aligned. So this can be a problem. And then intensity fluctuations can also cause lasers to change. This is just the perfect case. But with this in mind, we go ahead and we now combine the beams for 4 different values of the intensity ratio, where we look at I1 specifically. And remember that I2 over IT is just going to be 1 minus I1 over IT. And so here, with most of the energy, or most of the intensity being 2, we end up with this pattern. We can still have this bright low. The ring down here is a little brighter in the simulation than it is in the experiment, but it is present. We move a little bit closer towards 50-50 here, and we start to see that this bright dot becomes a bit of a ring. We still have this here, the ring down here has become brighter, although it's not quite slanted like it is in the simulation. Here it becomes more pronounced, at closer to 50-50, and we start getting that ring structure that we were seeing for psi plus in the previous slide. And then finally, with more of the energy in I1 and I2, we end up with a smeared ring, or smeared like crescent, and sort of the ring structure we were seeing earlier. Just for edification, I plotted the discord of the, or of the sort of belt state for these eigenvalues, and inset the simulation figures where they would end up lying on that. And so this is where we would expect a discord measurement to put the discord, for instance. So we see at 50-50, we get the lowest discord, but as we get closer to all of the light being one to the other, we get higher values. This would mean that there's more non-classical correlations in those two states, and in this state, classical correlations and the quantum correlations, basically. Or rather, there's basically no quantum correlations. Okay, so as a conclusion, I've noticed that a lot of the talks today have to do with analogies between either quantum mechanics, classical mechanics, or other kinds of analogies. And I think the takeaway is that these analogies sort of create a cross-pollination of science, where in classical mechanics, developments of new devices and macroscopic demonstrations can allow us to learn more about quantum mechanics and find new things to explore. Likewise, in quantum mechanics, we can find new effects and a deeper understanding of the theories, even in quantum mechanics, that allow us to develop new devices and sort of create this loop. As an example, in classical mechanics, we've been able to develop new electron beam devices for doing electron ballistics based on some of the similarities between those and the propagation of light. In quantum mechanics, the study of these analogies has led to the Photonic Hall effect and analogies to Anderson localization in scattered medium. There's a lot of more examples of quantum classical analogies in this wonderful book by Dragon and Dragma. I think this board here serves as a good example of how these can sort of be. If we can develop better devices for measuring discord, or better techniques for measuring discord, that improves our understanding of the quantum mechanics and sort of the locations where this might be useful. But being able to then study those tells us a little bit more about the boundaries that exist between classical and quantum mechanics and what the actual differences between the two are. So I guess that's it. Any questions?
Yeah, so we recently did a little bit of Rhodes calculus in our balance class. So the idea of the point cluster and the analysis of box can make sense.
Yeah.
But I think where I got confused about was how for a position basis vector that the point cluster is about polarization.
Yeah. So we've added another degree of freedom, which is not unheard of. So basically, we've just tensored the position space with the polarization space, right? So we just created a bigger product space.
All right, I think we should move on to the next speaker, who is